Hello viewers, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. In today's video, let us discuss about eigenvalues and eigenvectors. First, let us discuss about eigenvectors and eigenvalues, and in the later part, we solve some of the problems related to these concepts. First, let us consider a system AX is equal to lambda x, where A is a matrix and X is a vector. Actually, AX transforms the vector X into another vector. So A transforms the vector X into another vector. Now we are interested in special kind of vectors X such that AX is parallel to X, or the resultant vector must be some scalar multiple of the vector X. So we are focusing on such vectors with the given system A. These special kind of vectors are called eigenvectors. Ax is equal to lambda x is obvious for zero vector. So for any zero vector, Ax is zero vector and lambda x is also zero vector. So if x is zero vector, this equation is obvious. So we are interested in non-zero x such that Ax is equal to lambda x. Such x is called eigenvector, and the lambda used in that equation is called eigenvalue. Let us have a detailed definition a little while later. Lambda x is equal to Ax, that implies Ax minus lambda x is equal to O, the null matrix, and this can be written as A minus lambda I x is equal to O, after taking the x as common, of course. This is another matrix form. If A minus lambda I is singular, is non-singular, then the only solution for this x is zero solution. So x will be a zero vector. So A minus lambda I x is equal to O. The solution for this is nothing but the null space of A minus lambda. Let us assume that A minus lambda I is some b. Now it is in the form of bx is equal to O. So the solution for this one is nothing but null space of b. B is here A minus lambda I. So if this matrix B or A minus lambda I is non-singular, then the dimension of null space A will be 0, and hence x is equal to only 0 vector. So we are not interested in 0 vectors. We are in search of non-zero vectors x such that Ax is equal to lambda x. So to find such x, this A minus lambda I must be singular. So to find non-zero vector x such that Ax is equal to lambda x, the matrix A minus lambda I must be singular. That means the determinant of A minus lambda I must be equal to 0. And this equation is known as characteristic equation. And the polynomial A minus lambda I is called the characteristic polynomial, of course. Let us further view this point through some of the examples. consider a matrix 0, 1, 1, 0. Now this is our A. Then let us find out for what values of x. Ax is equal to lambda x. So we need to find x such that Ax is equal to some scalar multiple of the x. So if we check, if we multiply 1, 1 with this A, we will get 0 into 1 is 0 and 1 into 1 is 1. 0 plus 1 is 1 and 1 into 1 is 1. 0 into 1 is 0. So 1, 1. So this is our x and this is the resultant vector. It is again x. So here our lambda is 1. Ax is equal to x, so lambda is equal to 1. So now we can say that this is one of the eigenvector for this matrix 0, 1, 1, 0. Similarly, in the place of 1, 1, if I take 2, 2, again I am getting 0 plus 2, that is 2, and 2 plus 0, that is 2. So if I take 2, 2, vector 2, 2, 2 and 2, the resultant vector is also 2. So this is another eigenvector. So in this case also the eigenvalue, the scalar, is 1. Here lambda is 1 in both the cases. So lambda is equal to 1. The eigenvalue is 1, and these are the eigenvectors 1, 1 and 2, 2. Similarly, any CC where C is a scalar is an eigenvector for this matrix A, that is 0, 1 and 1, 0. Let us take another vector 1, minus 1. So if I multiply the given matrix 0, 1 and 1, 0 with this 1, minus 1, I will get minus 1 and 1. So this is 0 into 1 is 0, 1 minus 1 is minus 1. So this is minus 1. So 1 into 1 is 1, 0 into something minus 1 is 0. So it is 1. Minus 1, 1. So this is minus 1 times of the x. This is nothing but minus x. So this vector x transforms into minus x after being multiplied by A. So our matrix A converting this x as minus x. So it is also multiple of x. Here lambda is equal to minus 1. The scalar lambda is equal to minus 1. So minus 1 is also an eigenvalue for the given matrix A. Similarly, if I take 2 minus 2, then I will get minus of 2 minus 2. So these are all. So the vectors of the form C and minus C, where C is a real number or scalar, all these vectors will be in the eigenvector space, which will be defined a little bit later. Right now, these are the eigenvectors. So here we can observe that this matrix A has two eigenvalues. One is plus 1 and another one is minus 1. So here we can observe that the addition of those two eigenvalues is equivalent to the sum of this diagonal elements. 0 and 0 is 0 and 1 plus minus 1 is also 0. So the sum of the eigenvalues is equal to the trace. We call it as trace. Trace is nothing but sum of the diagonal elements of the matrix. So that is one of the observation here. Let us look into some more examples before finalizing it. Let us consider one more example, 5 1 and 1 5. So here a minus lambda I. Let us find out the eigenvalues for this given matrix A. Let it be A. Then A minus lambda I is 5 minus lambda 1 1 5 minus lambda. I have to take the determinant here. So this will become 5 minus lambda whole square minus 1. That is lambda square minus 10 lambda plus 24. Here we can observe that this 10, of course here it is minus 10. So this 10 is nothing but the trace of the matrix. 5 plus 5 is 10 and this is 10. And this 24 is the determinant of the given matrix. 25 minus 1, that is 24. So it is lambda square minus of trace times lambda plus determinant of given matrix. This is the characteristic equation. And this can be factorized as lambda minus 6 and lambda minus 4. If we equate this to 0, that which is the characteristic equation of the given matrix A, that is that A minus lambda I is equal to 0 implies lambda minus 6 times lambda minus 4 is equal to 0, that is lambda is equal to 6 or lambda is equal to 4. So these two are the eigenvalues for the given matrix A. So these are some of the observations on some simple examples. Let us consider one more example. Let A is equal to 3 minus 2 1 0 and U is equal to minus 1 1 and V is equal to 2 1. Then AU is equal to, so A is multiplied with this U. So 3 into minus 1 minus 3 minus 2 into 1 minus 2 minus 3 minus 2 is minus 5 and 1 into minus 1 minus 1 and 0 into 1 is 0. So minus 1 minus 5 minus 1. This is the product of these two vectors A and U. A is the given matrix and U is the given vector. So AU is equal to minus 5 minus 1. Here we can observe that it is not a multiple of, not a scalar multiple of this U, minus 1 and 1. And if we observe AV, this is A and this is V is 2 1. 3 into 2 is 6 minus 2, that is 4. And 1 into 2, 2 plus 0 is 2, 4 2. 4 2 is a multiple of 2 1. 4 2 is 2 times of this 2 1. So this is 2V. AV is equal to 2V. Now it is in the form of AX is equal to lambda x. Here the lambda is 2. So eigenvalue is 2. And we can say that this V, that is 2 1, is an eigenvector for this matrix A. 3 minus 2, 1 0. And this U is not an eigenvector for the matrix A. So A only stretches or dilates V. So here we can observe that the given matrix A can stretch V here. but not u. U is going in other direction. So geometrically, this can be visualized like this. So this is our V. V is given as 2, 1. So 2, 1, that's why it is plotted here. After multiplying with A, AB is 4, 2. So it is 4 and 2. So we can observe that it is in the same direction. So the magnitude of V is enhanced by multiplying with A. Similarly, we can enhance the signal or anything. We can enhance or reduce by multiplying with a suitable matrix A. Here we can also observe that the matrix A can enhance V in a particular ratio, that is eigenvalue. Here 1 is eigenvalue, here 2 is 1 eigenvalue. And as per our previous observation, since the trace is 3, other eigenvalue will be 1. So 1 and 2 only the eigenvalues of this matrix. Of course, later we will prove this result also. So matrix A stretch or dilate V in a particular ratio, that is eigenvalue. Whereas in the case of U, so U is here, since it is -1 and 1, and AU is -5 -1, which is plotted here. So it is not in the direction of U. It is in a new direction. So A transforms U, but not in the desired direction. So U is not a eigenvector. Whereas AV is nothing but it's an extension of V. So such vectors are called eigenvectors, and the ratio is called the ratio, or the multiple is called the eigenvalue. This is the geometrical representation of eigenvalues and eigenvectors. So let us define eigenvalues and eigenvectors and eigenvalues. So eigenvector, an eigenvector of an n by n matrix A is a non-zero vector x such that Ax is equal to lambda x for some scalar lambda. So this relation Ax is equal to lambda x is obvious for zero vector. So we are not interested in zero vectors. That is why a non-zero vector x such that Ax is equal to lambda x for some scalar lambda is called an eigenvector of an n by n matrix A. Eigenvalue is that lambda. So a scalar lambda is called as eigenvalue of A if there is a non-trivial solution x of Ax is equal to lambda x. If Ax is equal to 2x, for some non-zero x, we can say that 2 is an eigenvalue of A. Such an x is called an eigenvector corresponding to lambda. That is, if Ax is equal to 2x for a non-zero x, then we can say that x is a eigenvector corresponding to the eigenvalue 2. So let us check whether the given vectors are eigenvectors of A or not. This is very simple. Let A is equal to 1, 6, 5, 2 and U is equal to 6 minus 5 and V is equal to 3 minus 2. Are U and V eigenvectors of A? So we need to check whether these two are eigenvectors or not. To check whether the given vectors are eigenvectors or not, it is very simple. We need to multiply with A, and if we get a multiple of the given vector, a scalar multiple of the given vector, then we can say that that vector is an eigenvector, otherwise not. So let us multiply A and U first. So AU is equal to 1652 times it is being multiplied by this vector 6 and minus 5, that is equal to 6 minus 30, that is minus 24. 5 into 6 is 30 plus 2 into minus 5 is minus 10. So 30 minus 10 is 20. 20 minus 24 and 20. And we can observe that this is minus 4 times of this vector U. So that is equal to minus 4 times of 6 and minus 5, that is minus 4U. Now it is in the form of Ax is equal to lambda x. Here lambda, the eigenvalue is minus 4. So the non-zero vector in that equation is an eigenvector. So here U is non-zero, so it is eigenvector of the matrix A, 1, 6, 5. Similarly, AV is equal to A times V. V is 3 minus 2. So 3 minus 12, 15 minus 4, which is equal to minus 9 and 11, but it is not in the form of a scalar multiple of 3 and minus 2. So we can't write as a scalar multiple of the vector. So that is not equal to lambda 3 minus 2 for any scalar lambda. So we can say that this is not an eigenvector of U. Thus U is an eigenvector corresponding to the eigenvalue minus 4, and V is not an eigenvector of A, since AV is not a scalar multiple of V. So to check whether the given vector is an eigenvector of the given matrix A or not, we just need to simply multiply with the given matrix and check whether it is a scalar multiple of the given vector or not. So geometrically we can see that this is our U and this is our V. So AU is also in the same direction. In the same direction. So U is eigenvector. In other words, we can say that AU is in the line joining origin and U in coordinate geometry. But in the case of vectors, U is a direction. This is the position vector. So AU is also in the same line. Of course, it is in the opposite direction since since the eigenvalue is -4 here. The direction is opposite, but it is on the same line. Whereas AV is not on the line joining origin O and V. This is the line. The multiples of V will be in this line, but AV is not here. AV is outside of this line. So we can say that AV is not equal to lambda V. So V is not an eigenvector of A. So similarly, we can solve some more examples. Is 1, 3 an eigenvector of 1, -1, 6, -4? If so, find the eigenvalue. Similarly, there is another problem. So let us go to our Excel lab where there is a simple program for this. So these are the problems. So the second problem is ready here. The given matrix is 5, 3, 2, 6, and -1 and 1 is the given vector. We just need to multiply these two. This is a simple program multiplying these two. Here you can see that. So after multiplying A and let it be U, AU is equal to, this is our resultant vector, which is 3 times to the given vector. So here it is 3. So 3 is our eigenvalue. Since it is a multiple of the given vector, we can simply say that this vector -1 and 1 is an eigenvector of the given matrix 5, 2, 3, 6. Similarly, we can check the first one also. So I am taking the first one, 1, 6, and -1 and -4. This is the given matrix. 1, 3 is the given vector. So after multiplying this, we are getting -2 and -6, which is -2 times of the given vector. So it is also eigenvector of the given matrix. See here, eigenvalue is -2. So similarly, we can solve 3 by 3 matrix problems also. This is another problem. Is 3 -2, 1 an eigenvector of -4, 3, 3, 2, -3, -2, -1, 0, -2. If so, find the eigenvalue. So these values are here: -4, 3, 3, 2, -3, -2, -1, 0, 2. And we are just multiplying this vector 3 -2, 1. So this is the resultant vector. This is matrix multiplication. This is simple matrix multiplication. -4 into 3 plus 3 into -2 plus 3 into 1. This is the simple program for that. And -15 is the result. Similarly, -10 and -5 are the entries of remaining. So here we can observe that this is -5 times to the given vector. So this is -5, and -5 is the eigenvalue. So this vector 3 -2, 1 is an eigenvector of the given matrix. eigenvalue is -5. Similarly, there is another problem. Let us check this also. 3 and 3, 5 in the first column. 6, 2, 6 in the second column. 7, 7 and 4 in the third column. And the given vector is 1, -2 and 2. So the resultant vector 5, 13, 1. This is the multiplication of these two, this matrix and this vector. This is 5, 13 and 1. This is not a multiple of this one. You can't find a lambda such that this is equal to lambda times this vector. Let it be B. So AB is not equal to lambda B. So there is no such lambda. So this vector is not an eigenvector of this one, of the given matrix. Similarly, we can extend these programs for any order n, and we can instantaneously find whether the given vector is an eigenvector for the given system or given matrix or not. So these are the problems which we have seen now. These problems are also seen there. So now this is another problem. Show that 7 is an eigenvalue of the matrix A is equal to 1652 and find the corresponding eigenvectors. So to check whether the given vector is an eigenvector, it is very simple. Just to multiply with the given matrix and to check whether it is a multiple or not, multiple of the given vector or not. But to check whether a number is an eigenvalue or not, we need to do a little bit of exercise. So the scalar 7 is an eigenvalue of A if and only if the equation Ax is equal to 7x satisfies. Let this equation be equation number 1. So this equation must have a non-trivial solution. Of course, zero solution is obvious everywhere. We are not interested in that zero solution. That is not, if x is 0, then it is not an eigenvector. We need to find a non-zero solution x such that Ax is equal to 7x. So this can be equation number 1. So Ax is equal to 7x can be written as Ax minus 7x is equal to O, or A minus 7i times x is equal to O. So if A minus 7i is denoted by some matrix B, then it is in the form of Bx is equal to O. So we need to just find the solution for the equation Bx is equal to O, which is nothing but null space of B. Here null space of A minus 7i. So to solve this homogeneous equation, form the matrix. So to find the null space, we need to find augment matrix. So let us first find out the value of B, that is A minus 7i. So this is our given A 1652. 7i, I is nothing but the identity matrix, 2 by 2 matrix here. So 7 into 1001, that is 7007. I am subtracting this from A. So 1 minus 7 is minus 6 and 6 minus 0 is 6. and 5 minus 0 is 5, 2 minus 7 is minus 5. So here we can observe that the columns are linearly dependent. This is minus 6, 5 and this is 6, minus 5. If you multiply with minus 1, you multiply the first column with minus 1, you will get the second column. So these columns are linearly dependent. So whenever the columns of the matrix are linearly dependent, we can find a non-trivial solution. So if this is converted into echelon form, the second row will be zeros, will be of zeros, and dimension of null A is not equal to 0. So it is more than 0. In this case, it is 1, of course. So whenever dimension of null space A is greater than 0, we can find non-zero, non-trivial solutions for the given homogeneous system of equations. So we can say that 7 is an eigenvalue. So to show whether a number is an eigenvalue for a given matrix or not, we need to form a matrix A minus lambda I, where lambda is the given eigenvalue, A minus lambda I, and from the dependence and or linearly independence of the columns of the matrix, we can say whether it is an eigenvalue or not. In the present case, both the columns are linearly dependent. The columns of the given matrix A minus 7i here, since 7 is the eigenvalue. So the columns of A minus 7i are linearly dependent here. So the system has non-trivial solution. So 7 is an eigenvalue. So to find the corresponding eigenvector, we need augment matrix. So it is confirmed that 7 is an eigenvalue. But to find the corresponding eigenvectors, let us form augment matrix A minus 7i O. That is, we are adding just zeros in the last column. Now this can be reduced into echelon form. So the first row can be divided with minus 6, so that the entries will become 1, minus 1 and 0. Similarly, the second row can be divided with 5. So the entries of second row are now 1, minus 1, 0. So this can be further equivalent to 1, minus 1, 0 and all zeros in the second row. Just by performing elementary operation, R2 goes to R2 minus R1, since both the rows are equal. So now this one is in echelon form and reduced echelon form also, of course. There is only one pivot, only one pivot column, first column. So we can, to find the null space of this one, we can convert this into equation form. So the equivalent equation is x1 minus x2 is equal to 0. So which can be further written as x1 is equal to x2. So the vector x1, x2 is equal to x1 can be replaced with x2 and x2 is x2. So this is x2 times 1, 1. So here x2 is any scalar The scalar multiple of 1, 1 is our eigenvector. So any vector in this form, x2 into 1, 1 or c into 1, 1, where c is a scalar, is an eigenvector of the given matrix A. So each vector of the form x2 into 1, 1 with x2 not equal to 0. If x2 is 0, then this will become 0, 0, a 0 vector. 0 vector is obvious, so it is not an eigenvector. As per our definition, we are not considering 0 vectors. So the vectors other than 0 vectors which satisfy the equation Ax is equal to lambda x are the eigenvectors. So the only condition is that x2 is not equal to 0. You can take any scalar. So any scalar multiple of 1, 1 other than 0 is an eigenvector corresponding to lambda is equal to 7. So this is the way how to find eigenvectors when the same are not given. Here it is given that 7 is an eigenvalue. It was asked whether 7 is an eigenvalue or not. They are asked to check that. So we have to check whether the given number is eigenvalue or not. This equation should have a non-trivial solution. We have checked that. So this is equivalent to a minus 7i. X is equal to O. And since these columns are linearly dependent, the dimension of null a minus 7i is greater than 0. So it has a non-trivial solution. So 7 is eigenvalue. So once it is confirmed that it is eigenvalue, then we are forming an augment matrix A minus 7i O, which is further converted into reduced echelon form. So which is further converted into equivalent equations, that is x1 is equal to x2. Using this relation, we can form the vector equation. x1, x2 is nothing but x2, x2, which is x2 times 1, 1. So any vector of this form is scalar multiple of C, x2 or C, where x2 is a real number or C is a real number. So these vectors will be the eigenvectors. So all such vectors is called eigenspace. So geometrically we can observe that this is 1, 1, and after matrix multiplication it is 7 times. It will become 7, 7. So any multiple of 1, 1, that is any vector on this line passing through the origin is an eigenvector, and each vector will be 7 times after multiplying with A. So this is the eigenspace. All the vectors in this line will form the eigenspace for lambda is equal to 7. So let us check these two problems also. Is lambda is equal to 2 an eigenvalue of 3238? Why or why not? Similarly, there is another problem. Let's go back to our Excel format. Excel lab. and check whether these two the problems are here. So here I am taking the second problem first. -1,469 is my A here, and I have to check whether lambda is equal to -3. Lambda is equal to -3. So this is A minus lambda I. This is A, and this is lambda I. We are subtracting this A minus lambda I, this from this one. -1 minus of -3 plus 3, that is 2. 4 minus 0 is 4. 6 minus 0 is 6. 9 minus of -3 is 12. So this is my A minus lambda. This is the augment matrix. A minus lambda I O. This is the augment matrix. And this is being converted into echelon form. So I'm making this zeros by using these columns. So here we can observe that this is a multiple of second row is a multiple of first one. So it will simply become a 0 row. So the columns of A 2, 0 and 4, 0 are linearly dependent. And the rank of A is 1, since there is only one pivot here. We have the rank theorem. Rank A plus dimension of null A is equal to n. N is 2 here. So dimension of null A is 1. That means there is a non-trivial solution for this system of equations. So lambda is equal to -3 is an eigenvalue of the given matrix. That is the solution. So we can further this 240 can be written as can be divided with 2. So x1 plus x2, 2x2 is equal to 0. That is the equivalent equation form. That will finally become, this will be the eigenvector. And any multiple of this one, any scalar multiple of this one will become an eigenvector. So this is the basis for eigenspace. Sorry, this is one of the vector in the eigenspace. Eigenspace corresponding to the eigenvector -3. Similarly, we can see the other problem also. So here I am taking 3, 3 and 2, 8. This is the given matrix, and lambda is equal to 2 is given. So A minus lambda is this one. Automatically it was calculated 1, 2, 3, 6, and this is also reduced into echelon form. Here also the columns are linearly dependent. So rank of A is 1. So dimension of A is 1. Null A is 1. Dimension of null A minus lambda is 1. So lambda is equal to 2 is an eigenvalue of the given matrix. Similarly, we can construct simple programs for higher order matrices also.